All right, guys, I wanted to do this video. I told you that I would do a short video that kind of demonstrates some of the alkyne chemistry that we're going to talk about. As I mentioned, alkyne chemistry is very similar to alkene chemistry, and most of the reagents are essentially the same. The outcomes are essentially the same too, but because of the extra pi bond, alkynes may do something just a little bit different, and so we're going to have to talk about some of those reactions where things are different. We will also then talk about how do we make alkynes, because remember, we didn't really have a whole conversation about making alkenes, because that was a whole chapter all to itself, or at least part of a chapter. And so what I want to do is make this short video that talks about some of the reactions that are essentially unchanged, that really don't have any sort of weirdness that are going on with it at all. And so it'll be fairly short. We'll talk about it, and then when we meet again, we'll talk more in-depthly about some of those reactions of alkynes that have a little bit of an extra consideration that has to take place. So let's go ahead and get into it, and we'll see what's going on with alkynes. All right, so alkynes are molecules with triple bonds, and like molecules with double bonds, alkynes do similar chemistry. So what I want to do is I want to talk about just those reactions that are really just no-brainers, that take the same sort of ideas from alkene chemistry and apply essentially the exact same products, and without really any new considerations to be made, or where the new considerations are really straightforward. And so let's start off with a couple of our first reaction, which is essentially the same reaction that we started off alkene chemistry with, and that's the addition of HX. So if I take an alkyne and I react it with one equivalent of HX, then I'm going to get essentially the same thing going on here. I'm going to get a Markovnikov addition of X. Now remember, I'm adding both H and X, but when I think about what the regioselective outcome, what I'm thinking of is that I'm going to get a Markovnikov addition of the X. So when I add one equivalent of HX, I get the exact same thing that's going on here with alkenes. I add X, I add it at the more substituted location. If I add one equivalent of HX to an alkyne, then I end up with an alkene instead of an alkane, but it's still getting an X in the most substituted location. Now, we talked about the mechanism of HX addition with alkenes, where we go through a carbocationic transition state, and we can essentially apply that same idea to alkynes. And I'm going to go ahead and draw out the carbons this time. And if I have HX here, then we can invoke this idea of at this point, a vinylic carbocation. Here, where then X minus would attack that cation and form the more substituted vinylic halide. Remember, vinylic and vinyl means attached directly to the double bond. Now, what we find is that in kinetic and mechanistic studies, that this mechanism isn't well supported. Now, first of all, if you remember, when we think about this carbocation stability, we remember that vinyl cations are particularly unstable. So if they're essentially essentially the same stability as primary carbocations, or maybe even less stable, then what you're saying is that we should see that that HX addition proceeds, you know, much more slowly than we would anticipate. In fact, it really doesn't anticipate, it doesn't proceed that much more slowly at all. And so it really does, that's one of the indications that makes us think, hey, maybe this really isn't the mechanism that's in play here. And you know, I'm really not going to make you, I really don't think it's incumbent for you to memorize or understand or know this particular mechanistic idea. But what they're saying is that it's actually a 3-molecule process where you have an alkyne and you get an HX and an HX. And you get a situation like this where it's happening with 3 molecules at one time. And so if you get to this, if you have this idea and this is what's in play, then you get this sort of 3-molecule transition state. Where you have this sort of partial bond being made to X, and you have a partial bond to H. And there's some cationic character here, and that means, you know, of course, we would say that if there's some cationic character, then the cationic character is going to be more stable at that more substituted location. And so, you know, if we think about it, this is a good explanation for the product. And kinetic studies kind of support that the rate is equal to the concentration of the alkyne times the concentration of HX squared. So we'd say that it is, you know, the third order mechanism is supported. You know, in truth, it's probably a little bit of mixture of the both. And at the end of the day, this is certainly true with a lot of reactions where, you know, we don't actually know 100% what's going on with a particular mechanism. We can offer a few mechanisms that are supported by experimental evidence, or at least not refuted. And then the truth is probably that that all these mechanisms are competing with each other, and maybe one mechanism is more important than the other. But at the end of the day, you know, it may be happening all together in the same pot at the same time. By and large and in general, you know, what you really should be thinking about and keeping in mind, and I think is the most helpful for organic chemistry, is to keep in mind that original mechanism for the HX addition to an alkene. If you think about that for an alkyne, then you really do have all the information that you need to kind of answer the question about, well, what kind of regioselective outcome is there going to be? And so you know at that point that the Markovnikov addition is what's going to proceed forward, and you're going to get the X added to the more substituted location. So again, that's, I think, exactly, or at least so similar to the reaction for alkenes that you know, there's really nothing new that's going on there other than the fact that it's operating on an alkyne. Now, you can use, as far as anti-Markovnikov addition, you can still get anti-Markovnikov addition, but it's only of HBr in the presence of peroxide. And you end up with an alkene. Though usually, what I want to say though is usually the trans product is the one that's predominant. Let me try to draw this correctly for the final time. There we go. And so the trans, or the, remember the E, the entgegen, the opposite stereochemistry is preferred. So remember, this is anti-Markovnikov, and usually the stereochemical consideration is that E is favored. So again, this is another reaction that's essentially the same as it is for alkenes. When you have an alkyne and you add HBr in the presence of peroxide, you get an anti-Markovnikov addition of HBr in this case. So you're, instead of having an alkane as a product, though, just like in the last case before, the alkene is the product. So you get a vinyl halide. In this case, it's in the anti-Markovnikov, or the least substituted position. And again, the stereochemical preference is for the E and the E stereoisomer to form. All right, so let's take another look at this. Let's take this same go back to this alkyne, and let's consider what would happen if instead of one equivalent of HX, we added excess HX. And so this is the outcome of this reaction, is you get the alkane back, but now we're just going to add X twice. That's all there is to it. And if we think about it, and if we kind of go back to that original mechanism that we said, is it perfect, but it's probably in competition with the other mechanisms that are going on, you're going to have an intermediate vinylic cation that's formed. Where X minus can come along and attack to form another intermediate product, which would be the vinyl halide. But of course, if you have excess HX, then we can come along and do the same reaction again, producing yet another cationic intermediate. Where then the halide can come along and add a second time to produce the final product. A product where you have R added twice. So this is called a geminal halide. And geminal means I've got two geminal, let's see, Geminal, and that means two halogens. Same carbon. And so it's a geminal dihalide. And so when we'll talk a little bit more about geminal dihalides when we talk about how to synthesize alkynes. But at the end of the day, if we take excess HX and we add it to an alkyne, we're going to get the addition of HX twice. The regioselectivity, or the regiochemistry, is still Markovnikov. And so that X adds at the more substituted location. And so there's another example of a reaction. Even though it does produce a product that we really haven't talked about before, we've got a dihalide, but it really is just a natural extension of the reaction of an alkene, or if you have enough HX around with an alkyne, and you form an alkene in the intermediate, then of course that alkene in the intermediate can go around and react again with HX in exactly the same fashion as we learned with alkenes. So there's not much going on there. not much going on new there. And so let's take another look at yet another example of a reaction where we have a addition reaction for an alkyne that's similar to something that we've already done before. And so this is the addition of a halogen. And so if you take X2, and this time I want to make sure that I specify the solvent, carbon tetrachloride, and I do one equivalent of this, then I'm going to add the X2 just like I did before. And if you remember before, it was anti-addition. It's anti-addition because of the sort of three-membered cyclic intermediate that was the halonium ion. And we looked at it in the case of bromine, and so it was a bromonium ion. But you get the same stereochemical outcome in this case for essentially the same reason. You could propose a mechanism that would involve a cyclic three-membered ring, and except this time it would have a double bond. So you can get an alkene that has two halogens attached across the double bond if you react an alkyne in the presence of X2 with one equivalent. But if you react that same alkyne with excess X2, then what's going to happen is you're going to add the halogen twice. And so you could still see where you would get an intermediate where you've only added the halogen once, but if there's more X2 around, then it can continue to add, and you would end up with a situation where you've added that halogen twice now. And so instead of having two halogen atoms on there, now you've got four halogen atoms on there. You've done it in the presence of excess X2, and so now you were able to add it twice. And so again, I think this is an example of a reaction where if you're familiar with the reaction of the alkene, and you consider of whether or not we're going to do it in excess or one equivalent, then at the end of the day, it really is not a big leap of new material in order to think about what the product might be of these reactions. You're still going to get anti-addition in the first case, where you do one equivalent of X2. And if you just add enough X2, then you'll get X2 added everywhere. And of course, you don't really have to have a stereochemical or regioselective consideration in this case, because you're going to remember there's going to be free rotation around this single bond, and so that's going to make all those conformations possible. So excuse me, I just saw that I forgot to, or I made a mistake and didn't have an R group there. I had an H there, so I just make a note that you then make a correction in your notes if you had copied that down like I had it written. Okay, and so there's one last reaction that I want to talk about, and that's halogenation. And so there are going to be two new reactions that we discuss that are somewhat different, but at the end of the day, they really are essentially hydrogenation, hydrogenation of an alkyne to add H2. And so if we think about the reactions that we already know, which is H2 in the presence of a metal catalyst like platinum or palladium, then if you add, you have to add two equivalents because we're going to add it twice. Remember, there will be an intermediate, and the intermediate will involve a cis addition or a syn addition of these two hydrogens. But this is not able to be isolated, so you can't isolate this. And so it continues to move forward, and we just add hydrogens everywhere, and you get it fully reduced. And so I don't think that, again, I don't think that's very different from this reaction, where I have H2 and platinum, and I fully reduce the double bond into a single bond. The same thing happens with a triple bond. I just need to make sure that I'm adding enough hydrogen to fully reduce the triple bond, but I'm going to add the hydrogen twice instead of just once. And keeping in mind, when I use H2 and platinum catalyst, I can't isolate the alkene intermediate. It goes on and reacts again because it actually is more reactive than the alkyne. So it's really difficult to isolate that. Now, you can, however, and these are where I'm going to introduce just a couple of new reactions. You can use a catalyst that prevents the alkene from reacting further. And the idea here is behind this is called a poisoned catalyst. I'm always spelling things wrong and having to flip back and look them up, making sure that I spell them correctly as often as possible so I don't embarrass myself too much. But at this point, if you've watched enough videos or you've been around me enough in lecture, my spelling is atrocious. At the end of the day, a poison catalyst stops the reaction from moving past the alkene formation. And one such catalyst is called, for this reaction, that will produce a cis alkene, that in other words, it does the same idea. We're going to use a poison catalyst. We're not going to reduce it any further than the alkene is a catalyst called Lindlar's catalyst. And so if I do this reaction, and it's still H2, but in the presence of a catalyst, but in this case, it's Lindlar's catalyst, then I'll add the hydrogen and form the alkene. Again, it's the cis alkene, but this is the final product. The final product is the alkene with the two hydrogens added in a syn fashion. So the stereochemical outcome is that we're going to produce what would be a cis isomer. But this is as far as this reaction goes. So this is essentially a new reaction for alkynes, where I'm producing a completely new product. In this case, it's an alkene. I'm using H2, which is still reducing the alkyne, but in the presence of a new reagent, Lindlar's catalyst, it stops the reaction at the alkene. It's poisoned from moving, it prevents it from moving further in the reduction process. So this is the product that you end up with. And so remember, this is syn addition, and you get the cis alkene. Now, so if you're thinking about this right now, okay, I've got a reaction. I can add H2 and platinum catalyst or palladium catalyst, and I can reduce the alkyne all the way down to an alkane. But what if I do want the alkene? Because remember, we've already started to talk about reactions of alkenes that then can produce a whole lot of different functional groups. And so this will be a jumping off point for all of those reactions of alkenes. But let's just say, for instance, the next thing you should be asking yourself was, okay, I can form a cis alkene, but can I form a trans alkene? And there certainly is a reaction where you can take a alkyne and you react it with sodium metal and liquid ammonia, and you get a reduction of the alkyne. It's still poisoned in the sense that it will not fully reduce to an alkane. It stops at the alkene, but you get anti-addition, and you produce the trans alkene. And so this is a new reaction, and it's a new reaction in the sense that you've never used sodium metal and liquid ammonia before. It's a completely new type of reaction. It's a completely new reagent. It is a reducing reaction. And I would suggest right now to think about this is that you're in the presence of a metal. And what you're going to see over and over again is that if you're using a metal, most likely the reaction will involve a reduction. And so this is called the dissolving metal reaction or dissolving metal reduction. And so that's one way to, if you think about it being a metal and that it's a dissolving metal reduction, and if you kind of put it in your mind that when you have a metal as a reagent, then a reduction is most likely to follow, then I think you'll be in good shape for sort of classifying these reactions as you move down the road. And so I think at the end of the day, those are the only reactions that I want to discuss that are completely the same. Or that are, I think, are very similar to the reactions in alkenes. And so to kind of give you a preview, there are a lot of other reactions that are similar. So we can think about the reaction of an alkyne with H2SO4 and mercury and water. And so, you know, if you thought about oxymercuration, demercuration from alkenes, you know that you ended up with a Markovnikov addition of an OH group. Now, this isn't specifically oxymercuration, demercuration. It is acid catalyzed hydration, but it has the same result as the acid catalyzed hydration and the oxymercuration, demercuration from alkenes. And so I'm showing you, you should see both, you have the acid and you have mercury as a reminder that this is the Markovnikov addition of an alcohol. And so what you get at the end of the day is something called an enol. It's double bond with an alcohol attached in the vinylic position. But we're going to have to talk about this one a little bit more. You can't isolate this one and it does something called tautomerize and form a ketone. And this is actually the final product. And so that's a little bit different, but you'll see that if you think about the fact that it forms an enol and what the enol does, tautomerize to a ketone, then you'll be able to say to yourself, okay, this really is similar to the alkane. Again, if you take another reaction that's a lot similar to the similar as the alkene, if you take another reaction that's similar to the alkene, hydroboration oxidation, and you do that in the presence of an alkyne, we're just going to change up the reagent just a little bit. Instead of BH3, we're going to do R2BH. So we're going to replace two of the hydrogens with R groups, but we're going to have the same second step. We've got sodium hydroxide and H2O2. You would say to yourself, well, I would get the anti-Markovnikov addition of an alcohol. And so I would still end up with an enol, but the enol would be at the least substituted position. But again, just to give you a preview, the enol is not isolated, and so it again tautomerizes. And you get an aldehyde at the end of the day. And so that's, that is a little bit different in the fact that, well, I have now R2BH instead of BH3. I don't have any THF listed here, but essentially it's the same reaction. Eventually we're going to talk about this more in depthly, but if you think to yourself, I'm still going to form an anti-Markovnikov alcohol, and in this case it would be an enol, then the only new thing is to think about, well, how does the enol then tautomerize to the aldehyde? In this case, it's an aldehyde. And so there's one other reaction I'll show you that's similar. And we're going to talk about it again more in depthly, but it's also oxidative cleavage. If I take an alkyne and I react it with O3 and water, in this case, it's just a little bit different. It's not DMS, now it's water. I still get oxidative cleavage. So I'm going to add an oxygen on either side of that triple bond, but because it's a triple bond instead of a double bond, it actually gets to add more oxygen. So in the case of the alkene, you end up with a ketone or an aldehyde, but in the case of alkyne, what's the more oxidized version of an aldehyde or a ketone? If you think about it, if you have RH, that's as most reduced as it can be. Then as you can oxidize, you get to an alcohol. Then as you continue to oxidize, you get to a ketone. And then as you continue to add carbons, now you have a carboxylic acid. And that's what you get in this case. You're going to get a carboxylic acid with one of the R groups, and you'll get a carboxylic acid with the other R group. And we'll talk about that a little bit more in a while, but at the end of or in the next video or in the next lecture. But at the end of the day, it's very similar. It's still oxidative cleavage. You still are breaking the carbon-carbon bond instead of a double bond. In this case, it's triple bond. And you're adding oxygen in that place. Before, where you just added one oxygen, now you're going to add multiple oxygens. And so I think that one is very similar as well. And so the other reactions involve forming alkynes. And then there's one brand new reaction that I'm not even going to show right now, but it involves the acidity of terminal alkynes and how you can turn that alkyne into a nucleophile and ultimately do an SN2 reaction where you form carbon-carbon bonds. And that'll be the sort of the first reaction that we talk about, where we can change the number of carbons in the chain. In other words, we can do oxidative cleavage to reduce the number of carbons. This will be the first time that we can add carbon. And so what I'll do is I'll start off with our next discussion, kind of just listing these reactions, especially the ones that we went over in the first part of the video. And after that, we'll move forward with a more detailed discussion on the ones that I mentioned in this video, and then really dig into some of those mechanisms that I didn't even write down in the video. And then we'll also talk about some of the reactions that I only mentioned in passing. So again, I'll see you soon.